Alright, purpose of this video is to discuss the situation of a car on an inclined ramp going in circular motion around a curve. And I'm going to look at different cases. For example, a case where there's no frictional force at all, a completely frictionless plane, and then one in which there is friction. So the way to handle that problem is to look at the forces acting on the car. And let's say this is the force due to gravity down this way. I'll call that one mg. And the other force is the normal force executed by the plane up in this direction, like that. Not drawn to scale here, but what I need to look at is what is the speed at which this thing can go in a circle and not slide up and down either direction on the ramp. And I can do that by setting up the following equations, where this is the normal force and this is the force due to gravity. So the component of the normal force that is causing the car to go in the circle is given by this vector right here. And by the way, this angle right here is theta. You can use Mr. Todd's rule to figure that out. This side's perpendicular to that side. This side is perpendicular to that side. So this component right here, Fn times the sine theta, is the component that is producing the centripetal acceleration. It is the centripetal force, so I can say that F sine theta is equal to m v squared over r, where r is the radius of the turn. I'm just going to indicate that by a vector here like that, the radius of the turn. I also have to have, for equilibrium conditions, that the vertical component of the normal force, this component right here, which is F sub n cosine theta, I have to have that Fn cosine theta has to be equal to the weight in order for it not to move up or down. Now I can quickly eliminate Fn from these two equations by dividing this equation by that equation, and I get that tangent theta is equal to mv squared over r divided by mg, like that. The m's cancel out, and that tells me then that v squared is equal to rg tangent theta, or that v is equal to square root of rg times tangent theta. So that's the first result. That's the minimum speed that I have to have, or the equilibrium speed I have to have, so that the car goes around the ramp without sliding this way or that way. And this will be the zero friction case. And just to be clear about this, in this zero friction case here, if you realize that if this thing goes faster than this speed, then the normal force is going to be greater than it is in this case, and that's going to tend to overpower the weight and cause the thing to slide up the ramp. And similarly, if I don't go as fast as this speed, then the normal force is going to be less than this, so therefore the vertical component will not offset the weight, which is kind of the way I have it drawn here, and this thing will slip down the plane. Alright, so now I want to consider the case where there's actually friction on the ramp. And let's take the case, first of all, where we want to find out what the maximum speed we can go at is so that it doesn't crawl up the ramp with friction. So if in fact I'm going fast and it's trying to crawl up the ramp, then the frictional force is going to act in this direction, opposing that motion. I'm going to designate that by a little f. So now I can write the equations. Since I have another force involved here, I can write the equations for equilibrium, namely that the force in the vertical direction, there's still the vertical component of the normal force, which is F sub n times cosine theta, and that has to offset both the force due to gravity and the vertical component of the frictional force. So I can write that as Fn cosine theta has to be equal to mg plus f, little f, times sine theta, since this angle here is also theta. Like that. All right, so that's one equation. And I also have that the centripetal force now is a component of the normal force, which is Fn sine theta. I have Fn sine theta, but I also have a component of the frictional force in this direction, and that's little f times cosine theta, and that is equal to mv squared over r, the mass times the centripetal acceleration. And let me rearrange this slightly and write this one as Fn cosine theta minus f sine theta is equal to mg, like that. That's this one and this one. But I also know that little f, the frictional force, is just equal to mu, coefficient of static friction, times the normal force. So I have two equations involving the normal force. I'm going to rewrite them here. I'm going to write this one right here as Fn times sine theta plus mu times the cosine of theta, because here I just substituted in here mu times Fn, and then I factored out the Fn like that. This is equal to mv squared over r. And from this equation up here, I'm going to write that one as Fn times cosine theta minus mu times sine theta, and that's equal to mg. And once again, I'm just going to divide this equation by this equation to get rid of the Fn. So I have sine theta plus mu cosine theta divided by cosine theta minus mu sine theta is just equal to v squared over r times g. And that means then that v is equal to the square root of r times g times this thing over here. And I'm going to abbreviate that with just s theta plus mu cosine theta, like that, divided by, I'm just shortening the notation here, minus s sine theta, where this is sine and this is cosine. So this is the maximum velocity that I can have with friction. Also take a notice up here of the picture again. Notice that if I consider the case where it's the minimum velocity. In other words, I'm slowing down where this thing is attempting to slide down this way, then this friction vector will be pointing up this way. And since the diagram's getting a little bit complicated here, I can just tell you that when you apply the frictional force in this direction and work through the same analysis, then you get down to the same exact equation, except the signs of mu are reversed. So I can just write down that V min is equal to the square root of R times G times sine theta minus mu cosine theta divided by cosine theta plus mu sine theta. And it's just would be a nice little exercise for you to work that out yourself, but I can tell you that's the way it works. But here's what you need to watch out for. Notice first of all that if mu is 0, i.e. the frictionless case, this term goes to 0, that term goes to 0, sine over cosine is tangent, and we're right back to the original no friction case up here. So that gives us a lot of confidence that these equations down here are correct. But what you want to watch out for, let's say that the coefficient due to friction is something like 0.7, let's say. Then, and let's say that R is equal to, say, 200 meters. G is equal to 9.81, and the coefficient of static friction for a dry road is equal to 0.7. When you plug those numbers into this equation right here, you get that V max is approximately equal to 64.85 meters per second. That's the answer for V max. And that works out to be, if you're interested, to about 145 miles per hour. Now here's the deal though. If you plug in 0.7 here, and I didn't tell you, but let's say that theta is equal to 30 degrees. Yeah, that gives you this answer, theta equals 30 degrees. But if you put 30 degrees in here and you put 0.7 in here, all of a sudden this becomes negative. And you say, oh, wait a minute, I can't have that. So what that's telling you is that even if you stop, you're still not going to slide down the ramp. So what you have to do is consider a coefficient of friction that is less than whatever the critical coefficient of friction is. It turns out that if you just stopped here on the ramp, then the critical coefficient of friction, mu, static friction, is just equal to tangent theta. So for theta equals 30 degrees, tangent of 30 degrees, that's equal to 0.577. So you have to have a coefficient of friction less than this, or it won't slide down the ramp even if it's just standing still. So if you want to work out this problem for a smaller coefficient of friction, then you can get a different answer. Let's say, for example, it's a wet road, then mu is about equal to 0.4. You can look up these numbers for tires on a wet road. It's about 0.4. So with mu equals 0.4, then Vmax worked out to be about 49.93 meters per second, and Vmin in this case worked out to be about 16.81 meters per second. And just if you care, This one is about 110.7 miles per hour, and this other one is about 37.3 miles per hour. So just be careful with this that you don't end up with a minus sign under the radical.